Welcome to this lecture. This is the first lecture of week 3. Before we proceed, let us first quickly recall what we have done in week 1 and 2. In week 1, we looked at the collection of events corresponding to a random experiment, or more generally, certain collections of special subsets of a general non-empty set. And we configured or we looked at certain structures like fields, sigma fields and monotone classes. We also studied the properties of these classes or collections of sets. In week 2, we entered this area of measures. We introduced this topic, and the idea was that we wanted to understand which events were more likely to occur or which sets are larger in size. To understand this, we assigned these numerical values to these sets. We obtained set functions, but since our motivation is to look at these sizes of sets or likeness or appearance of certain events, we looked at these special structures which we called as measures. We studied these algebraic properties, continuity properties of measures, and in particular we restricted our attention to probability measures because this is what we are interested in. Okay, so these are what we have covered under the materials in week 1 and 2. So as before, let's switch over to the lecture slides and start the discussion in the for the materials in week 3. Okay, so this is the motivation to look at certain type of functions on sample spaces. So in many random experiments, the outcomes are numerical, and as we are interested in these numerical outcomes, numerical values, numerical features, we need to consider these functions defined on the sample space omega. Okay, so we are looking at functions for each point or each sample point in the sample space. Alright, so we are looking at these values assigned to each sample point, and we are looking at these collections of functions. On the other hand, there are certain random experiments where the outcomes are non-numerical. For example, in tossing a coin, the outcomes are either a head or a tail. So now you will ask, what is the value? But in practice, you associate certain values to these heads or tail, you assign certain meaning. For example, when you toss a coin, you might be calling heads, and if head appears, you win the toss. So there is this notion of winning a toss and losing a toss. So therefore, there is a physical meaning associated to these outcomes which are heads and the tails. So just to understand this better, it is sometimes useful to associate certain values to these non-numerical outcomes like head or tails. So what you can do, you can associate the values +1 and -1 to head and the tail, and you can think of this +1 and -1 as winning once or losing once, or winning 1 rupee and losing 1 rupee. So you can interpret it in this fashion, and therefore now the interpretation is much more quantitative. It's in terms of certain values. So this is what we are going to restrict our attention to. So no matter what kind of outcomes we have, we will typically associate certain meaning to them which will be numerical, and we are going to study those values and get some more intricate features or intricate analysis of the corresponding random experiment. So in regards to this discussion that we are having, what we are going to consider are functions of the form small f with domain sample space omega and the range space real line. Okay, so we are looking at real valued functions on the sample space, and to do this analysis that we really want to do, we require more structure on this function. So you cannot just start looking at this arbitrary type of functions which are real valued and defined on the sample space. You need certain nice regularity structures on these functions. So this is what we are going to discuss in this lecture. Okay, so this is in terms of certain measurability structures associated to the domain space and the range space. What we are going to do, so since omega is the sample space of a random experiment. It comes with a collection of events which we have already associated the structure of sigma field. So on the domain side, you have the structure of a measurable space, so omega script f. So this you can think of as the sample space together with the collection of events. On the other side, the range side, you have the real values, and on the real line we have discussed extensively about this sigma field, which is the Borel sigma field. So what we are going to focus on are certain structures with these informations that you have already collected, like these sigma fields scripted f on the domain side and the Borel sigma field on the range side. So with this in hand, we are going to look at certain specific structures of these functions f. We are not going to look at arbitrary functions f. So recall from note 6 of week 1 that for a function which we can consider now a general function, mapping from a domain space omega 1 to a range space omega 2. So omega 1 and omega 2 are some non-empty sets, and you look at an arbitrary function defined on top of that. Now if you fix a subset A of omega 2, the range side, then you can define the pre-image of this set under the function small f. This we have defined in note 6 of week 1. So what was this? Let's quickly recall that. So we looked at this f inverse of A defined by all points in the domain. So now the domain is capital omega 1. So you are choosing all points or all points omega 1 coming from the domain side, such that the value associated to those domain points, the f of omega 1, the associated value, lands up in the set capital A. So f inverse of A, that is nothing but the pre-image of A, which is defined as all points in the domain side such that the values of the function on those points lands up in the set capital A. Okay. So remember, f inverse here does not represent the inverse of f, because a priori whenever you are taking a function, it's not really invertible. So you don't know whether the function is 1 to 1 on 2, you don't know anything like that. So here you should treat f inverse of A as one symbol instead of treating it as two separate symbols like f inverse and A. So you should think of it as one big symbol signifying this pre-image for A. Okay. So now here f inverse, you can now think of it as a function that associates any subset on the range side to its pre-image, or this is now connecting or associating sets from the range side to the domain side. So this you can think of as a function in that sense, but this is not the inverse function of the function f. Okay. Now if the function f has an inverse, then of course you can connect the notion of this inverse with the actual inverse of a function, that you can try to work it out. But now what we are interested in are properties of these pre-images. So the properties of pre-images comes in this form. So take this general function which starts in the domain omega 1, lands up in the range omega 2, and choose a collection of subsets from the range side. So I belongs to lambda, so where lambda is some index set. So here it's some arbitrary set, it could be finite, countable, uncountable, anything. So it's just some arbitrary index set. So you are looking at a collection of subsets of omega 2. You are not associating any structure of any type. So function is general, a collection of sets is general. Now what we are discussing now are properties of the pre-images of the sets AI under the function f. So what are the properties? So the first property says, no matter which set you take, if you look at the complement of the pre-image, so f inverse of AI, that's a set on the domain side, if you look at the complement, that can be again identified as a pre-image of another set, and that turns out to be the pre-image of AI complement. So this is a nice fact, you can try to prove this. Similarly, there are these nice properties that connects the unions and intersections over these indexing sets. So here we are looking at that same index set lambda. This is some arbitrary index set, and it simply says that whether you take unions or intersections of the pre-images, these unions or intersections can simply go inside. So by that I mean, if you are looking at the unions of all pre-images, it's nothing but the pre-image of the unions of AI, and intersections you have the similar result. So try to prove this. So these are some very nice useful observations about pre-image of a set under the function f. Now with this in hand, we are now focused at the pre-images of sets coming from the range side, and we are going to look at certain properties which restrict the collections of functions on the sample spaces. And with this, we now arrive at the first definition. So we are going to talk about measurable functions. Let omega 1 f1 and omega 2 f2 be two measurable spaces. So I take two measurable spaces on domains omega 1 and omega 2, and I already need to have sigma fields on top of them. So I have script f1 and script f2, the appropriate sigma fields on these domains. Now I look at a general function f from omega 1 to omega 2. So with domain omega 1, range omega 2. So we say that this function is f1 over f2, script f1 over script f2 measurable if for all pre-images we land up in the domain side. So you take all subsets that are on the range side sigma field, which is the script f2. So you take all such subsets which are in the range side sigma field, look at the pre-images. Those pre-images I want them to be on the domain side sigma field. So this is the restriction we impose here. And if it so happens for a function f defined on a domain omega 1 to the range omega 2 with this associated sigma field script f1 script f2, if it so happens for such a function, then I am going to call it script f1 over script f2 measurable. So this is the definition. This is the restriction that we impose on a general function. So if it happens, then we introduce this concept of measurability. Now in many situations there are standard choices of sigma fields. So for example, you can start with a finite sample space, and then you see that the power set is a natural example of a sigma field there. On the real line, we have extensively discussed this Borel sigma field. These are certain natural choices. So once you have these natural or standard choices, you typically like to work on only these type of sigma fields. So you will put these natural or standard choices on the domain side and the range side as appropriate. So if in any discussion the sigma fields are kept fixed, then for simplicity we may simply say that f is measurable instead of saying f is script f1 over script f2 measurable. Okay, so 2 points to note. First thing is that there may be standard choices for sigma fields, so we will use that. But once you have these standard choices, the sigma fields are now understood from the context. Once you have these standard choices, the sigma fields are understood from the context. Then for simplicity of the notation, you will simply say that f is measurable instead of explicitly mentioning these sigma fields script f1 script f2. So for example, on any of these sides, on the domain side or the range side, if the real set of real numbers appear and you are going to use the Borel sigma field, then you can ignore that and don't mention it. Just say that f is measurable. This will be understood from the context that you are using the Borel sigma field. So this is the simplicity of the notation. Now we focus our attention to the specific case when the range side is the real line. So as discussed above, so when you are looking at certain random experiments with numerical outcomes, you exactly get this type of a function. So each sample point gets associated a real number. Otherwise, if the random experiment appears with non-numerical outcomes, you will associate certain meaning or values to this numerical values, and therefore obtain these type of functions such that it's defined on the domain omega and the range side is the real line. So as motivated like that, we are going to focus our attention to the case of functions which are defined on domain omega, the sample space, and the range side is the real line. So in the next definition, this is explained in more concrete detail. So we are looking at a specific type of measurable functions now. So what is this? So now the domain side is fixed, that is omega script f. So that is some measurable space that is given to you It may be coming from a random experiment, or maybe you can look at some general non-empty set together with some appropriate choice of a sigma field. So that gives you a measurable space, and that you are going to put on the domain side. On the range side, as discussed, we are going to look at the real line, and we will be considering the Budel sigma field on top of the real line. So that will give you the appropriate measurable space on the range side. Now look at the measurable functions which comes out from these conventions, from these choices of measurable spaces. We say that the function f, which is defined on the domain omega with values in the real line, to be script f over Br, the Budel sigma field, measurable, or simply Budel measurable if the same condition that you take now all Budel sets coming from the real line. So you are looking at all Budel subsets of the real line, which is on the range side. You are looking at all such sets, looking at their pre-images now. The pre-images are subsets on the domain side, and you want those subsets to be in your collection script f. If it so happens, you are going to call this function small f as script f over Br measurable, or for simplicity of notation, you will simply say it's Budel measurable. So you are going to talk about Budel measurable functions on domains omega, and the idea is this, that once the range is real line and you are talking about the Budel sigma field, you don't have to mention it explicitly once more. It's understood from the context. So you are looking at, for all sets on the range side, all Budel subsets on the range side, you are looking at their pre-images. These pre-images must fall in the domain side collection, the sigma field script f. So if this happens, you are going to call it a Budel measurable function. So notice that before defining these measurability concepts, we are fixing the sigma fields. So this you have mentioned earlier, that we have also talked about the standard choices of sigma fields and other things. Now we have always fixed the sigma fields on the domain and the range first before defining the measurability. What is the reason for this? The reason is this: if you change the sigma fields on either the range side or the domain side, you will be getting different types of Budel measurable functions. So if you make a specific choice of sigma fields on the domain side and the range side, you will get some type of functions which will turn out to be measurable with respect to those sigma fields. But then if you change the sigma fields either on the domain side or on the range side, you might get other functions which will now turn out to be Budel measurable or measurable, and you might get certain functions which were measurable in the earlier sense but no more in the for the new sigma fields. So you have to be careful with these choices of sigma fields. Once you make these choices, before your discussion, you always make these choices, keep it fixed, and then continue on the discussion. So we are going to do this. We are also going to use this shorthand notation or the statement. What does it read? It reads as follows: small f maps from omega scripted f or Br. What does it mean? You are explicitly stating the domain and the range, which is the domain is omega, range is R, but you are also putting in the sigma fields, appropriate sigma fields on the domain side and the range side. So just to be clear, the function, the given function, is purely a function defined on the domain. So for each point in the domain omega, you are associating a real number. So that's how the function is defined. But whenever you are talking about the measurability, you have to mention the appropriate sigma fields. So what you do, whenever you are talking about this measurability, you explicitly state that. So that this notation is now explaining these choices. So you simply write f from omega f. It's as if it's coming from that appropriate measurable structure on the domain side and lands up on the measurable space on the range side. So that is R Br. Okay. So that's how the measurability should be explained. So if you write this, then it will mean the Budel measurability of small f is exactly as per the above definition, meaning you explicitly specify the sigma fields. If the sigma fields are understood, then you can remove it, you don't have to mention it, but it's always good to keep track of the sigma fields on the domain side and the range side. And to do that, we are going to use this term f from omega f, omega script f to RBR. That notation that function is measurable. So we are going to write this statement. With this introduction of measurable functions, we are now ready to talk about examples of Bodel measurable functions. So let's start with the simplest example that you can think of. So you take a measurable space omega script f and fix a constant. So the simplest function that you can think of is a constant function. So what you do? So for all points in the domain omega, you associate the value, that constant value, small c. So that gives you a constant function on the domain. Now you are going to ask, is this constant function a measurable function or a Bodel measurable function? So on the domain side, you have already been given some arbitrary sigma field, arbitrary but fixed, script f. So that's a sigma field that is on the domain side. On the range side, you have the real line, which is of course having the Bodel sigma field. And with these two specific choices of the sigma fields, you are going to talk about the measurability of the function. But now what you need to do? You are going to choose subsets, Bodel subsets from the range side. So here you are going to choose these sets capital A, and you are going to look at the pre-images of those sets. So it turns out that when the function f is just a constant function taking the constant value c, then the pre-images f inverse of A, that can be only two possible things. What is this? So it depends on the choice whether the constant value is in the set A or not. If the constant value is not in the set capital A, then the pre-image turns out to be an empty set. If the constant value is in A, then the pre-image turns out to be the whole set. Why is this? So again, go back to the definition. What is f inverse of A? You are going to look at all possible points in the domain such that the f of omega, that value, lands up in the set capital A. But for this specific function, the constant function, f of omega, no matter what omega is just a constant c. So therefore, if your constant value c is in the set A, then you are going to get all points in the domain side as its pre-image, because all those points are landing up exactly in C. So therefore f of omega is in A, right? So therefore you get the whole set. But if the point small c is not in the set A, then the point is that f of omega is never in A for all possible omega in the domain side. So therefore you end up with the empty set. So now you get these two possible cases for the pre-images. So no matter what capital A you are choosing, you always end up with these two choices, either the empty set or the whole set. But then if you take any arbitrary sigma field, it will always contain this empty set or the whole set. That's by construction, by definition, and hence the pre-images are always in the sigma field no matter which Bodel subset you choose from the range side. So for all possible Bodel subsets, if you look at the pre-images, they always fall in the domain side sigma field, and therefore it turns out to be Bodel measurable. So this is therefore Bodel measurable, or f script f over BR measurable for any choice of sigma field. So this is happening because the empty set and the whole set is always in the sigma field. So that is what I have already explained. Please try to write it down. I have left this as an exercise. So please check that no matter which sigma field you choose, constant functions always remain Bodel measurable. Okay. So now you are interested in some more general functions. So we have already introduced these indicator functions of sets, and that's what we are going to look at next. So take a measurable space and choose some subset on the domain side. So B is a subset on the domain side. So let's take some arbitrary subset. It need not be in the sigma field script f. Alright. So now look at the indicator function. So how is it defined? So for all point in the domain, all you need to check whether the point is in the set B or not. If it is there, you associate the value 1, otherwise you associate the value 0. It's simply a 0-1 valued function. Alright, that's the function. Now you want to check that given this choice of script f, sigma field on the domain side, you are going to check whether this function, this indicator function, is measurable or not. So again, what you need to do, you are going to choose these Bodel subsets from the range side. So take these sets capital A, and you are going to look at the pre-images, and you are going to check whether the pre-images fall in your sigma field on the domain side script f. Alright. So now what are the possible cases? So you can now check, as done for the constant function case, that you can split it into 4 possible cases. So for the constant function case you had 2 choices, but now you have to look at these 2 values, zeros and ones, and with these possible choices, if zeros and ones belongs to A or 1 does not belong to A and so on, so you have these 4 possible choices, you will get these different sets. If neither of 0 and 1 is in A, you are going to get empty set as the pre-image and so on. Please check this. This is left as an exercise for you. Alright. But then what do you want? You wanted this indicator B to be measurable. Now remember, these 4 possible options are all these things that will appear as the pre-images. Now remember that a sigma field script f always contains the empty set and the whole set. So you don't need to worry about these 2 things. But a priori you do not know whether the sets B or B complement is in the collection script f. So to check that indicator B is measurable, what you need to check, the set capital B is in the collection script f. Alright. So I am saying that if you start with the assumption that B is in script f, then you can show that indicator B is f over B are measurable. Why? Because if B is in scripted f, then B complement is also in scripted f, and therefore all possible pre-images for Borel sets will land up in your domain side sigma field script f. So therefore indicator B will become Borel measurable. On the other hand, if you start off with assuming Borel measurability of the function indicator B, then you must have these pre-images B or B complement to be in your sigma field, and that simply reduces to the condition B belongs to script f. Alright, so please try to write it down. I have already explained the ideas. Alright, so therefore for indicator of B to be measurable, where B is a subset on the domain side, the set B must be in the sigma field. So what is the interpretation now? So we saw that the constant function is measurable with respect to any sigma field that you choose on the domain side. But when you went to a non-constant function, this indicator B takes 2 values. So whenever you shifted away from the constant function, immediately there came some restrictions on the measurability conditions, right? So for this to be measurable, this to be Borel measurable, you only need to choose those sigma fields where the set B is included. If you don't have the set B in your sigma field on the domain side, then indicator B will not be measurable. So that's what we have discussed. So therefore this already puts some restrictions on the sigma fields or on the other side on the measurable functions. So therefore first you always guessed constant functions as measurable functions, but whenever you move on to specific choices of sigma fields, then for non-constant functions you have to be very careful, and it is very important to identify which are the non-constant measurable functions given the situation. So given the appropriate choices of the sigma fields that you start off with, you always should try to identify whether there are any non-constant Borel measurable functions. Okay. Now with these 2 examples at hand, we are not really satisfied. We would like to obtain more examples. So now in what follows, we are going to discuss a large class of examples. What do we do? So we consider functions with range R, but the domain is also taken to be R. So we are taking R2R functions, and we are going to talk about Borel measurability of such functions, meaning you are going to put Borel sigma field both on the range side as well as the domain side, because both domain and the range are the real line. We are going to make this choice, and we are going to talk about the Borel measurability here. Now you can check that if you take a continuous function, then you can look at the pre-images of all open subsets and it will turn out to be open. So if you start off with a continuous function, it will imply that pre-images of open sets is open. On the other hand, if you assume this condition that the pre-images of all open sets is open, then you can show that the function is continuous. So this is an if and only if condition. This is a statement that comes from the real analysis. Please try to work this out. Now using this exercise, we get this nice collections or large class of examples for Borel measurable functions, but with the domain real line. So this result follows using principle of good sets, which we had discussed in note 22 of week 1, and combining with this exercise that we have mentioned about identification of continuous functions with this pre-image conditions for open subsets. So if you use the continuous functions, if you look at the continuous functions on the real line, then using the principle of good sets, what you can show is that these continuous functions turn out to be Borel measurable. So you get a large class of examples. So here what we are doing, we are looking at real valued continuous functions on the real line, and we are choosing the Borel sigma fields on both sides, the range and the domain, and we are saying that if you take a continuous function, then it's automatically Borel measurable. So that's the statement of the proposition. But since this requires this principle of good sets, which we have skipped earlier, we are not going to discuss the proof. We are going to assume this as a fact, and we are going to use this. So for concrete examples of concrete continuous functions and hence measurable functions, you can choose to look at polynomials with real coefficients. So if you choose any polynomial with real coefficients, they will turn out to be Borel measurable, right? Because these are continuous functions. Moreover, you can think of other nice continuous functions like trigonometric functions like sine functions and cosine functions. They are also continuous functions defined on the real line, and therefore they will turn out to be Borel measurable. So therefore, you have a large class of examples immediately after you get this proposition. And other than that, we have discussed these two examples. One was the constant functions, another was the indicator functions. So we are going to continue these discussions for Borel measurable functions, but we are going to look at functions taking values in higher dimensions, in Euclidean spaces, higher dimensional Euclidean spaces. This we are going to discuss in the next lecture. We stop here.